Hello, welcome to the afternoon session of Web Directions Code. The name of my talk is Put on Your Asynchronous Hat and Node. My name is Marc Fasel, and indeed I work for Shine Technologies, and Shine Technologies is a boutique software consultancy here in Melbourne. And we do enterprise and mobile development, and the enterprise development we do with a range of technologies like Node.js, but also Rails and a lot of Java. I'm a senior consultant there, and my personal interest is in high-performance websites, hence my involvement with Node.js. So what you may be asking is, what is an asynchronous hat? Well, I'm not really sure what I was thinking about, but it's maybe something like this. But the reason why I chose this title is because in software development, we often use this term of putting on a different hat in order to signify that certain tasks that we do in software development require a totally different mindset. And I believe asynchronous programming requires such a different mindset, and so maybe it's kind of fitting to put on that mental hat, that asynchronous hat. So the topic today is Node.js. And Node.js is our trusty server-side JavaScript platform. So it's JavaScript on the server side. And it uses event-driven, non-blocking I/O to make it super fast. Because Node.js is not just your JavaScript environment, but it's also it's an environment where you can build multi-user, highly concurrent applications with. And similar to the front end, Node.js uses a single thread in order to run your JavaScript, and the way it achieves that high performance is by moving all the I/O operations and offloading them to the operating system, so the operating system can take care of those. The reason it chooses these I/O operations is because they take a really long time. So this, just as a comparison, if you're doing something in memory and in the CPU in comparison to an I/O operation, the I/O operation will not be a factor 10 or 100 slower, it's 100,000 times slower. So you can do 100,000 operations in the, inside the CPU in comparison to one I/O operation. So to offload these I/O operations outside that main thread of execution for JavaScript is the reason why Node.js is so fast. And the way it achieves this is by using, making the I/O all asynchronous. So I/O operations are things like accessing the database or accessing the file system or making communication, HTTP communication requests, responses. So all of that is I/O and all of that is asynchronous while the rest of your code is still synchronous. But that's basically why it's so fast. And since most of the stuff that we do on the server side is actually I/O, really asynchronous is everywhere when you're dealing with Node.js. So that's the reason why asynchronous programming is particularly interesting in Node.js. Now, synchronous programming and asynchronous programming to me are different mindsets. Synchronous coding, I believe, comes pretty natural. The order of execution is exactly the order in which you specified the code. And it doesn't matter in synchronous programming if your code is a long-running, let's say an I/O operation or not. The execution of code will stop exactly at the operation and wait until the result comes back so you can use it in the next line of code. So that's a very natural execution order that it goes in the way you specified it in your file. Asynchronous coding, on the other hand, is a little bit more difficult in terms of the control flow and the flow of the order of execution. That typical serial execution where we have one after the other, one operation after the other, and possibly each operation will depend on the result of the previous operation, is the serial execution is actually a bit unsightly if you program it in asynchronous. coding, and it leads to some unsightly nesting. So that is a very typical, that's your typical use case of programming is the serial execution, and it actually looks pretty ugly in asynchronous code. On top of the serial execution, we also have some parallel execution where we can fire off asynchronous I/O events, multiple asynchronous I/O events in parallel, and that's something that we usually don't use in synchronous programming, that we fire off operations in parallel. So this is something new in asynchronous programming that you kind of have to get your head around. There are concepts of asynchronous functions that take a single callback and some asynchronous functions which are event emitters that you need to consider. And one of the things that you will also see in asynchronous programming, that error handling becomes much more explicit than what we have in synchronous coding. So if we look at some synchronous code, this is actually code that can run in the Node.js server, so this is JavaScript. And I said previously that all I/O operations are asynchronous in Node. That's not completely true. There are some asynchronous operations that have synchronous counterparts, and they're more for easing your way into Node.js programming, but not for your high-performance computing, because that's going to slow down your server too much. But I'm going to use some of these synchronous counterparts of the asynchronous I/O operations in order to show how synchronous code differs from asynchronous code. So here we have some synchronous code. The first line uses that synchronous counterpart of read there, a function, an I/O operation in Node.js, and it takes one parameter, a directory, and gives us back an array of file names. And then we iterate over the file names and log them out, and then we log another message done. So that's synchronous code, and we see that the looping in the second line depends on the result of the first line. So we first have to have the file names before we can do the loop. And in synchronous code, the operation would be blocking on the read dir sync until we get something back. And now to visualize that is, you can imagine that in computer time, this synchronous operation takes 100,000 times longer than any of the other lines of code that we have here, so a lot longer. So this would be blocking, but that's our synchronous code. Now, if we want to convert that to asynchronous code, we use the readdir function of Node.js, and it takes as the first parameter, again, our directory that we want to read, and as a second parameter, a so-called callback function, which is called as soon as the asynchronous operation is done. And the way this asynchronous, the asynchronous operation works is that fs.readdir will hand over the asynchronous operation to the operating system, which will run it in parallel, and the callback function will be registered in Node.js to be called when that asynchronous operation is done, and the operating system gives us back a done event for this operation. And then the callback function is called by Node.js's event loop itself, so by Node.js itself. So let's look at some more synchronous code. So this is another example. So let's say we have now our file names, we read our directory, the file names in our directory, we have an array. Now we could use, for example, fs.stat_sync in order to get some statistics on each of the files, and use that in order to count the total number of bytes in a directory that all the files make up. And that would be our synchronous code. And what we see here, so we're firing here, we have, let's go back. Yeah. So here we have a loop, and the loop stops each time it hits that synchronous code, waits for a very long time until it gets a stat back, and then counts up the total number of bytes. If we want to make that asynchronous, we could make that into this new parallel execution, because really the gathering of the statistics for each file is independent from each other. So we can actually run these the stat on the different files in parallel. So hand them over, fire them off as asynchronous calls, register their individual callback functions, and then just wait as callback functions come back. So this would be an example of that parallel execution in asynchronous code. And the yellow part that I marked here shows that we do need to do some extra plumbing code in order for that to work, because we need to figure out when all our parallel asynchronous calls actually come back. And we do that, in this case, by having a counter that is initialized before to the file name's length, and is counted down each time one of the asynchronous function is come back, and only when the counter is 0, we are actually done and we can log out the total number of bytes. So this is a type of stop criteria that you need to introduce if you're using parallel execution in asynchronous code. Now, I think the examples that I've shown so far are relatively straightforward. You move the code a little bit around and add maybe a stop criteria. But when you start doing asynchronous programming, you will soon see that code like this comes out. And this is called the pyramid of doom, because you're nesting asynchronous function. The yellow ones are asynchronous functions. They're all nested inside each other, and the code keeps on moving further to the right until you can't read it anymore, and then you're doomed. It's also called callback hell by some other people. So what we see here is that our standard serial execution, where one command depends on the output of the previous command. In this case, we're doing a copy type of operation where we read a file and then write it to a destination, and then change the file permissions on there. So each one of them, of the asynchronous function, depends on the result of the previous function. And if that is the case, we need to nest them inside their respective callback functions, and that's how we get this nesting. So this is a very typical thing that you have to do in programming, is the serial execution. And this is how it looks when you do it in asynchronous programming, and it gets ugly quite quickly. But fear not, my talk is going to have some solutions on how to handle this type of serial execution. So another one of the main building blocks of Node.js is the event mechanisms. So events are the notifications that we get from our asynchronous function we passed on to the operating system. The operating system will send us events if we need to be notified of anything. In a simple case, it would be the done event for the asynchronous operation. So events are used for that asynchronous communication. They're sent back to Node.js, and Node.js will take the event, look at the callback function that's registered for it, and run the callback function. So events are used for asynchronous communication. In Node.js, there are two different types of asynchronous functions. There's some of them that take a single callback function, and that means that our asynchronous function only has one single done event, and we attach that callback function to that. And in the more complex case, when an asynchronous function emits multiple events, we use a construct called an event emitter, and that allows us to attach more than one callback functions to the different events. So how does that look? Single callback function is our standard case. 80% of the API from Node.js, the I/O operations are all single callback functions, asynchronous functions that have a single callback. And we've seen that already earlier in the slide. fs.readdir is such a asynchronous function, and it takes the directory as the first parameter and the callback function as the second parameter. And what we can see now in the callback function, we can see that we have to deal with a failure case and a success case. So in the case of our single callback function, we actually have to mix our standard successful application code with our error code. And that's one thing where asynchronous programming differs quite a lot from synchronous programming. So our second type of function that we have in Node.js is the event emitter asynchronous functions. So in this case, fs.createReadStream would create us a read stream for a file, for example. And here we can see the notation is readStream.on. So we're using the .on method in order to attach callback functions to different events. And one of the advantages of event emitters is that the event emitters always have an error event, and so your error code can actually be in one logical place rather than polluting it with your application code in all the other events. So that's an advantage of having an event emitter, but as I said earlier, there are only about 20% of the functions that Node.js has are actually event emitters. But that brings us to an interesting point, the error handling. If we compare synchronous error handling, we have the concept of exceptions, and exceptions give us a lot of goodies that make error handling a lot easier, and we come to know and love those. In asynchronous programming, we'll see that exceptions are not a good idea to throw, and also some of the some of the things that exceptions give us is that that there's some automatism, that we don't have to actually write any code in order to do certain parts of the error handling, while in asynchronous code we have to write explicit error code everywhere, and unfortunately or fortunately lots of it is boilerplate. It's always the same code, but it has to be in there, and this asynchronous error handling code leads to more confusion in the pyramid of doom because you have to put it in each of the callback functions. So let's look at synchronous error handling, how we do it in synchronous code. Here we are blessed with exceptions. Exceptions do a few things for us. One of the things that we get without having to program anything, when an exception is thrown, the execution of our code stops immediately. And that's really a nice thing. That means that without actually doing anything, we certainly prevent any run-on errors. So if one method errored out, then it's most likely that the methods that follow it may also cause errors because they depend on code, on data that was produced by the first method. So this immediate stop of execution is actually very nice. Exceptions also give us this automatic bubble up the call hierarchy, so we can actually choose a place within our application where we want to put our error code. Wherever we want to catch that exception, we can put our error code. So the error code becomes logically separated from our application code, and that we all get by using exceptions. Let's look at an example for some synchronous code. The world with exceptions. So if we have a function read file that consists out of 3 operations, open file, read content, and close file, if there's actually an exception thrown in one of them, the read content, if there's no error code in the read content function, then it will bubble up to the next level, to the read file, and there's no error handling code there either. And then it will bubble up to the bottom part where we actually have a try-catch block and actually could catch the exception and put our error code exactly there. Now, this is the world with exception in synchronous code. There was actually a world before exception in synchronous code, and I remember that time. And here's an example. This is still JavaScript, but here I'm trying to do the same thing without actually dealing with exceptions. And what you end up having to do is for all your operations, you have to extend your signature to add an error object or some kind of parameter that notifies the calling function that an error occurred. And then you have to evaluate that error object with each and every operation of your synchronous code in order to stop those run-on errors. So you have to do extra error handling code in there. It's always boilerplate. It's pretty straightforward, but it's just as much error handling code I have to put in here than actually application code. So that's if you have to deal with situations where you don't have exceptions. Now let's look at asynchronous error handling. This is something that you may be tempted to do that seems to make sense at first, that we have the situation that we have an asynchronous operation read file that takes our callback function. The callback function has an error object, and if an error object is set, the asynchronous function failed, we may be tempted to throw an error, and we may be tempted to put a try-catch block around the fs.read file in order to catch that error. But in terms of the execution, it's actually the try block will be executed, then the fs.read file fires off that asynchronous function and registers our callback function, and then returns back the control to that main part, and we land in the catch block. But since no execution was thrown at this point, it will just go through the catch block and do nothing, right? So with this asynchronous call, the exception will actually be thrown much later whenever the callback function is called, and that's not in the same call stack anymore. It's actually the callback function is called by the Node.js event loop, by the main loop that Node.js runs. So if we throw an error in the callback function, then that will bubble up to the event loop of Node.js and actually stop the complete Node.js server. So even though exceptions are possible in asynchronous code, they certainly don't do what you want, and there's pretty much no way to use try-catch in this scenario in a sensible way. So asynchronous error handling is certainly different. So how do you do it in asynchronous code? Very similar to our world before exception example. Pass around an error object and put a lot of error handling code inside your asynchronous code. So for single callback methods like read file, in our callback method, there's a convention for Node.js that the first object is always an error object, and it's filled whenever the asynchronous operation failed. And we have to evaluate that error object every time we write a callback. And so we have error code in every single callback. Now if we compare that to event emitter error handling, it's a little bit better because, as we've seen earlier, that event emitters have that error event, and we can put our error code in a single place rather than mixing it with our application code. So we can have a look at our pyramid of doom with error handling. So that's what you have to do when you're writing asynchronous code. You always have to put that error handling code in there, and it's very much boilerplate. It's actually the same code everywhere, but you have to put it in there. Although, because you don't have exceptions, you cannot stop the execution thread and deal with it at some other place. So, in summary, with asynchronous error handling, you can't catch exceptions that happen in callbacks. You always have to write explicit code to handle error. In case of the simple callback, we have error code that gets mixed with the application code. And in the case of the event emitter, we actually have a separate place to put the error code. Now we've seen some of the rough edges. That kind of showed some of the rough edges of asynchronous programming. The error handling is a bit tedious, and the pyramid of doom will possibly get your head spinning a little bit because of the deep nesting. But help is actually available. That's if you're using vanilla Node.js with the simplest way of structuring your code. There's some things that you can do yourself, and one of them would be to pull out the callback functions and making them named callbacks, And so far we've always used an anonymous function as a callback function, that last parameter. But there's no problem in making that actually an explicit function with the same signature with the error and file names, and put the code, our callback code, in there, and that already makes our code a little bit more readable. We're looking at the nesting of named callbacks. Here again we have this, this nesting of, if we want to copy a file, we first have to read it and then write it. And the code does look a little bit better without using, if we don't use those anonymous functions. So that's one of the things that you can already do to make your code more manageable again. Another thing that you can do is you can use control flow libraries. And control flow libraries fix those problems that we saw earlier, deal with our serial execution that leads to nesting, and the parallel execution that needs that stop criteria. And really, when people start with asynchronous programming, the control flow is really the first thing that they want to fix. That really causes them some eye cancer. And so it is actually not very difficult to fix that. You can write a library like that for yourself. And subsequently, there are many, many control flow. Many people have tried this. And for the module manager from Node.js, you'll have hundreds of control flow libraries available. And how they help you with the control flow, I'm going to show on the example of one of the more popular ones. It's called Async.js, and Async.js is actually used by very many of the third-party modules that other people have written for Node, because they ran into exactly the same issue with the control flow. And Async.js has been called the underscore of asynchronous code, underscore being our Swiss Army knife of helper functions to deal with our synchronous code. And Async.js takes some of these functions, a subset, and allows us to use them in order to control the flow of our asynchronous code. So Async.js roughly is divided in two blocks. There's some control flows constructs that help us with the control flow of our asynchronous programming, and there's some functional constructs that we can also use to in certain use cases. So this is an example of code when we use Async.js. We have this async.series construct, this async.series function that takes an array of other functions. We see two functions that are in an array. On the bottom, a function done, which is, so this construct means that async will execute these two asynchronous functions in series and then call the done function. So by using asynchronous, all of this is still non-blocking. You just don't have to nest it yourself. Async does it in the back. But if we look at the code, we can see that the asynchronous function is the one fs.mod, change the file permissions. So that's the asynchronous function itself. But in order to use it with async, you actually have to wrap it in another function, in an anonymous function that has a callback parameter, and then do some magic plumbing code for async to work. So you have to wrap the actual asynchronous call in some other function. And that is plumbing code that you need to do in order for it to work. Once these async calls these functions in series, so one after another, and at the end of calling all the functions, it will call the last function, the function done. And, or actually there are two scenarios when async will call the done function. That's if all the function have executed in the series, or one of them has errored out. So the done function again needs to check for the error object and deal with the error case. And so it's both for the error case and the success case. But that makes our code look a little bit more nice, even though we have to put a little bit of plumbing code around it. That's for the serial case. Parallel is very similar. If we want to run asynchronous functions in parallel, we wrap them up in this in that function again called async.parallel, and it will fire them off in parallel, and we don't have to worry about any stop criteria. Async will notify us either if all of the parallel calls, asynchronous calls, have come back, or one of them has errored out. So that kind of helps us a little bit with the pyramid of doom and the nesting of serial asynchronous functions. Next to the control flow that we just saw, async.js also has some functional constructs that are very nice to use. So if we take the first line, async.map, it has an array of parameters that are applied to an asynchronous function, fs.stat, and the result of that is an array of the results of this asynchronous function. So we will get an array of stats for each one of the files. So that's an easy way to call an individual asynchronous function with a number of parameters. Async filter is kind of similar. You take an array of parameters, apply it to an asynchronous function that returns true or false, and according to the value true or false, it will the result will be only those elements in the array for which the asynchronous function returned true. We also have an async reduce that is very similar from the way it handles the asynchronous calls. So now we've seen we can do a little bit ourselves by naming callbacks. In order to structure our code better, we can use a functional, a control flow library like async.js in order to structure our code better. But we can also use something called promises to structure our asynchronous code, because really promises is a pattern for asynchronous control flow. And yesterday we already had Tony explain to us what promises are and some of the give us some of the examples, and I will show how you can use promises in Node.js in order to tame your asynchronous control flow. So from the definition, promises are objects representing a future outcome of an asynchronous call. So it means that promises are an alternative to our asynchronous function. We actually wrap that asynchronous function inside a promise object, and that enables us to pass the promise around. We actually have an object that represents it, and we can then attach callback event handlers to two outcomes, two basic events, a resolved and a rejected, basically the success case and the failure case of this asynchronous call. And that's what promises give us. They wrap an asynchronous call in an object and allow us with some syntax to attach those callbacks. So far it's not very exciting, but hold on. Later on the exciting part comes. Let's look at first how we turn a callback into a promise. So here we have a function getReadFile promise, which does exactly that. It calls that fs.readFile asynchronous function, and somehow through some magic turns it into one of those promise objects. And the way it does that, I'm using a promise library and implementation of this concept of promises, the Q library, the same one that Tony was talking about. And you have to go a little bit, you have to first create a so-called defer object, and a deferred object, so we do that with q.defer. And the defer object is really a wrapper around the promise that allows us to set, to call reject and resolve on that promise. The promise has only those two states, reject and resolve, but it don't have methods for rejecting and resolving the promise. And the reason why this is separated is so that you can have some parts of your code who are allowed to reject or resolve the promise, while other part of the code can only observe whether the promise is rejected or resolved. So here we need to get the deferred object, and In the fs.read file, in the callback function, what we do, if the callback function had an error, then we call deferred.reject with that error in order to reject the promise, and we call deferred.resolve if the promise is successful and we pass the data in. So the way this is executed is basically that we call that getReadFilePromise function. We get our deferred object, we fire off our asynchronous call, and immediately return control to that function and return the promise. So now we have a promise, and we can imagine that our asynchronous call will take forever, and now we have that promise, and now we can continue and attach those callback handlers to that promise. And so we do get read file promise to get that object, and then we use the so-called then notation in order to attach a resolved and a rejected callback. So far, it's still nothing special. It looks like just a different syntax in order to attach callbacks to an asynchronous function. But the cool stuff about promises is promise chaining, because if you want to run multiple asynchronous calls in series, you may wrap each one of them in a promise, right? And then chain them together with that then operator, because there's, in the specification of promises, it says if a then method returns a promise, then you can call then again on that promise, and this way you can chain them. So if we look at the top example, we first get our read file promise, then attach a write file promise as when the promise is resolved, when the first asynchronous call is done, a write file promise, then a change file permission promise, and we can keep on going like that. So that is our serial execution case that we had earlier that was so difficult to code in asynchronous code, and it starts looking a lot nicer without any of the plumbing code that we had in async.js. We can also do very similar, do parallel execution. That's the bottom example, where we pass in an array of promises, and if you call in the Q library q.all, what we get back on q.all on the array, what we get back is a promise that will be resolved if all of the promises are resolved, meaning all the asynchronous calls are back, or will be rejected if one of them is rejected. So the cool thing about promises is this chaining of promises one after the other. It becomes syntactically pretty nice. Promises have another thing that's quite nice, and that's error handling. Now we saw before that promises, the then operator takes two callbacks, one for resolved and one for rejected. But you don't have to supply that rejected callback. You can just leave it out. It's an optional parameter, and if we do that in this case, we have read file promise. We attach a single resolved promise to it, a callback with a promise to it, and then another one, another resolved callback, and an error callback. And with promises, if an error occurs in one of the promises, if one of them is rejected, it will go down through the hierarchy until it finds a callback, an error callback, and will call that. And that gives us some kind of exception-style error bubbling that we didn't have before because we couldn't use exceptions in asynchronous code. So promise is a pretty nice concept. They really help us with the asynchronous control flow, avoid the pyramid of doom by using this chaining of then, and allow us some exception-style error bubbling. So this brings me to the conclusion of this talk. I hope what I've shown is that asynchronous programming needs some kind of different mindset, a different hat. There are a few new things that you have to wrap your head around. Some of them already exist in front-end coding, but in Node.js they become more, you just have to go head-on with asynchronous programming, so you really have to wrap your head around them. Stuff like callbacks, event emitters, the explicit error handling that we see. But this is just if you're starting off with Node. If you're getting into trouble, for the more difficult part, you can actually help yourself by using named callbacks, and that'll help you a little bit with the control flow. Or you can use control flow libraries like Async.js to tame your code, or you can go with promises, which give you both the nicer control flow as well as some exception-style error bubbling. And that concludes my talk for today. Thank you.